Okay, we are going to spend just a little bit of time developing a very simple numerical application. The problem of interest that we want to solve is we live in a house with walls made of a certain material, and we're going to experience a very cold storm overnight, and the question is whether or not the pipes in the walls will freeze. This problem can be solved by solving numerically the one-dimensional heat equation, which is given here as the partial temperature with respect to time is proportional to the partial temperature, second partial temperature with respect to space. In this equation, use temperature, x is distance, t is time in seconds, and alpha is a property of the material called the thermal diffusivity. It sort of describes how quickly heat can flow through the material. And what we seek is a numerical simulation to model this equation. So first step we have to do is take the continuous equations and discretize them. In this case, we discretize the left-hand side and the right-hand side independently, and we approximate continuous derivatives with difference equations. So over here on the time axis, we set up a spacing in time, delta t, and then we can approximate the derivative of the temperature in time by a simple difference, the temperature at time instance k plus 1 minus the temperature at time instance k over the spacing in time. And similarly, we take the right-hand side, we discretize the second derivative using a second-order difference formula and spacings in x. When we do this, we're effectively creating a mesh for the simulation. Here we're showing the time axis and the distance axis orthogonally in temperature upwards, and the parallel lines represent lines of constant time or lines of constant distance, and where those lines cross are the points at which we're actually evaluating or solving this partial differential equation. So if we take the left-hand side of our approximation of the left-hand side first derivative and the right-hand side second derivative and set those equal to each other, then we can solve for the temperatures at time instance k plus 1 in terms of the temperatures at time instance k. So our task now is to use this update algorithm, which I've duplicated here in the upper right corner of the slide, and implement the body of this function, given that the array of doubles UK1 is the array we want to compute, and the array of doubles UK is the doubles at the last instance, and all the other parameters as specified, spacings and boundary conditions. So let's do that. We start by editing. I'll keep this equation present here, and we'll start by editing ftcs.c, where we have the body of this function. Now, I forgot to mention, I should have mentioned, this algorithm is known to be stable only for values of r less than 1/2. So we add a little logic here. Actually, it's less than or equal to 1/2. So we're evaluating, going back to this equation, we're coming up with the temperatures at time instance k plus 1 in terms of the temperatures at time instance k. and these should all be actually UK zeros. So there's our numerical implementation of this update equation. But we have one additional requirement, and that is to impose and maintain boundary conditions. And if we get this far, we believe we've computed a good solution. All right, so we've now implemented that. Let's make our application. Now, once we make the application, the question is, how do we know that what we've written here actually makes sense, actually does performs what the calculations we expect it to perform? This is a problem in general for numerical software, and as a result, a lot of numerical packages come with a lot of test suite and test results to compare against. And so we've done that with this application as well. And so if we just type in make check, so in order to test this particular application, we've already set it up with a previously known result, previously good known result in that file there. So if we just run make check, it will compare against that result and let us know if the code we've written is working. And so I'm going to assume that everybody got passed here when they ran their code, but if you didn't, instead you got failed, then you've probably got to look at your software a bit and figure what you might have done wrong. For reference, you can find the code on the lesson page. So now that we have implemented our algorithm and we've checked it to make sure that we believe it's working, let's use it now to solve the problem of interest with a number of simplifying assumptions. We'll assume that prior to the storm, the temperature has been the same temperature on the inside and outside at 70 degrees Fahrenheit. The overnight storm will last 15.5 hours, and the temperature low will be minus 40 degrees Fahrenheit. Our walls are a quarter meter thick of solid wood, and the pipes are 0.1 meters in diameter, and we'll say the pipe will freeze if the center point drops below freezing. So you can get help on how to actually run the application by typing in the application name and -- help. It prints you out all of the parameters, command line arguments, and how to run them, and it actually gives you some example command lines and how to run it. So what we need to do is run it for our case and get a result. And so what does that look like? Our walls are made of wood, so the alpha is 8.2 times 10 to the minus 8th. Length of the wall is a quarter meter. $15.5 hours is 55,800 seconds. The overnight low boundary condition is in Kelvin, minus 40 degrees is 233 degrees Kelvin. The boundary condition inside the house is 70 degrees Fahrenheit, which is 290, what is it? 294 degrees Kelvin. And the initial condition is going to be constant at 294 degrees Kelvin. And let's set the name of this run to be oops, got the parentheses wrong on that. Okay, so it ran, created the resultant wall there. So now let's, once we've run the application, how do we actually assess whether or not the pipes are going to freeze? You can do this in a couple of ways. The low-tech way is look at the results curve. I don't know if you can make heads or tails from that data there, whether or not it's frozen where the pipe is. But if we do this, we get this result, and this is showing us the wall from 0 to 0.25 meters, and the y-axis is the temperature, and it shows us where the pipe would start and end in the wall, and the freezing point of Rother right here at 273 degrees Kelvin. So does this temperature curve at the center of the pipe drop below freezing? It does not. So after 15 hours the pipe hasn't froze, and we conclude that our water pipes will not freeze when this storm passes.